this lecture, we'll continue to learn about alkenes by looking at the chemical reactions that they can undergo. When we talk about chemical reactions in organic chemistry, we're often interested in the actual mechanism that explains how the reaction happens. You've seen a lot of chemical reactions, especially in general chemistry, but you may not have ever thought about why they actually take place. A mechanism in chemistry is an explanation of how the chemical reaction happens at the molecular level. And it's different from a chemical reaction because it has a lot more detail. In this unit, because we're covering alkenes, we'll see a lot of reactions in which an alkene reacts with another molecule. Here's a general example. On the left side, we have two reactants, an alkene and a molecule that has two atoms, A and B. On the right side of the arrow, we have our product. This is a chemical reaction because it shows us what we start with and what we end with. And it's helpful if that's all you need to know. But it's problematic if you want to understand how we got from the reactants to the products. It's a little bit like having all the ingredients to make something and a picture of what you want to make, but not having an actual recipe. So let's look at how this recipe or mechanism works in organic chemistry. And I'm just going to pick one as an example. For instance, if I wanted to draw the mechanism for the reaction at the top of the screen, I'd have to understand how the electrons are actually going to move. Well, in this particular case, it's all about understanding how negative and positives attract. We know that a carbon-carbon double bond is an area where we find 4 electrons. Those electrons would be attracted to any other positive area. If the molecule AB had a dipole with a positive and a negatively charged atom, that would allow us to actually initiate this mechanism. The electrons in the double bond would be attracted to the positively charged atom. We draw an arrow to represent the movement of the electrons. This would show that the electrons in that bond would like to move towards A. In that process, the electrons that were connecting A and B would be transferred to the atom B. That would be the first step in this mechanism. After that step has taken place, here's what it would look like. Essentially, we've broken the double bond because we created a new bond between one of the carbons and the atom A. In the process, we've also created a carbon that only has 3 bonds. We know that this is unstable. That's because this carbon actually has a positive charge, and it's what we call a carbocation. You might remember from general chemistry, cation means something with a positive charge. In addition to the carbon-containing molecule, we also have whatever B was. B now has 2 electrons because the bond between A and B broke. This is a very unstable state. It's what we call a transition state. And we usually put it in brackets and use this little double T sign to indicate that it's simply a transition state. It would exist for mere microseconds in the real world. So what happens next? Well, again, many mechanisms are driven by the attraction of opposite charges. In this case, we now have a positively charged carbon, which is very unstable, and we have the negative area of this electron pair. Those electrons would be attracted to the positively charged carbon, and when they join up, that creates another bond. This is an example of a chemical mechanism because it uses arrows to show how the electrons would actually move. One of the things that's very powerful about mechanisms is because they explain why a reaction happens, you can figure out if any given reaction would actually happen given any 2 molecules. Another thing that makes them very powerful is they explain why sometimes we don't get what we want from chemical reactions. For instance, this transition state's very unstable. Perhaps it'll react with something else than simply the atom B. That's the reality of organic chemistry, and it's one of the reasons that organic chemistry can be such a complex topic. However, as I promised you at the very beginning of the quarter, we don't want this to be a really complex class. And for that reason, we're not going to cover mechanisms in any more detail. I'm basically going to teach you how to do chemical reactions in organic chemistry, but we'll leave the mechanisms out. Having said that, at any time, if you have any interest in learning these mechanisms, they are fascinating and they really illuminate what's going on at the molecular level, so don't hesitate to ask me. As you can probably guess, I get a little excited when I get to draw out a mechanism. But for now, let's just focus on these chemical reactions. One thing you'll notice that's different about writing chemical reactions in organic chemistry than general chemistry is that we use a lot of shorthand. We've already seen examples such as how we condense many molecules so that we don't have to write them out in too much detail. There's other types of shorthand you'll notice as well. One thing that's very different is that when we write organic chemistry reactions, we often like to simplify them by writing things like catalysts, simple reactants, or reaction conditions right above the arrow that's in the chemical reaction. It would look something like this. If you saw an arrow in a chemical reaction with H2O written above it, that indicates that water was used in the reaction. It was either a reactant or it was a catalyst. We also use it to indicate things like reaction conditions. Let's look at another example. This is another way that you might see information given to you in an organic reaction. Not surprisingly, the formula on the bottom, H2SO4, sulfuric acid, means that sulfuric acid was either a reactant or a catalyst in this reaction. The fact that it's on the bottom doesn't necessarily mean anything special. The triangle on the top is actually the Greek letter delta, and because delta usually indicates things like a change in temperature, we use it as a shorthand way to indicate that heat is added to a reaction. So if you want to tell someone to heat this thing up while you do the reaction, you draw a delta over or under the arrow. One other thing you might notice is sometimes we like to manipulate the pressure that we do reactions under. Here's an example of how you'd show that. In this reaction, ammonia, or NH3, was a reactant or a catalyst in the reaction, and the information on the bottom of the arrow means that the reaction was done at a pressure of 1500 kilopascals. I won't expect you to have all these memorized, but I just want you to get a sense of the fact that we really can simplify our reactions by just including things above or below the arrow. It's basically a type of shorthand. Another way that we can shorten our chemical reactions in organic chemistry is by leaving off molecules that we don't think are important. You have to be a little bit careful doing that, but generally if you're dealing with a product that's inorganic, usually something like water, it's pretty much okay to leave that off. Same as if you have a byproduct, meaning something you didn't really intend to produce and isn't actually that important to why you're showing the chemical reaction. So many times very simple molecules like carbon dioxide and water are left out when they're products. Be careful, however, not to leave these off if they're reactants. That makes them very important to the meaning of the reaction. Finally, something you'll see over and over again in organic chemistry is the use of the letter R, a capital R to be specific. The capital R is used when you want to show that a molecule has a carbon chain, and you don't really care whether it's a methyl, ethyl, propyl, or any other group. So R is a general thing that we use to mean put a carbon chain here. For instance, here's a molecule of cyclohexane that has a branch. Instead of having a methyl branch or an ethyl branch or a sec-butyl branch, I've just written the capital letter R. That means this doesn't matter if the R is a methyl, an ethyl, or any other carbon-containing chain. So R is just a general catch-all letter we use when we don't really care what we're writing. Now let's look at some specific examples of organic reactions that alkenes undergo. The most common type of reactions for alkenes are what are called addition reactions. And as we said in our last lecture, addition reactions mean that you're adding new atoms to a molecule. One of the most common reactions in alkenes is what's called hydrogenation, and we touched on this briefly when we looked at fats. Hydrogenation is the addition of hydrogen, usually in the form of hydrogen gas. Let's look at a general example of a hydrogenation reaction. To keep it as general as possible, I'm going to create a carbon-carbon double bond, but on these other bonds touching the carbon, I'm going to put R. Technically, it would also be okay for any one of these, or all four of them, to be hydrogen. But to keep it simple, let's just write R. Remember, that means we have carbon chains, or as I just said, hydrogen would be fine as well. When we do a hydrogenation reaction on an alkene such as this, we're going to add H2. To use shorthand, I'll just write H2 over the arrow. If you apply hydrogen gas to an alkene, nothing happens. That's because hydrogenation actually requires a catalyst. Without the catalyst, the reaction won't happen at all. And you have your choice of two catalysts that are quite famous for this reaction. One is platinum, which has the chemical symbol PT, and the other is palladium, which has the chemical symbol PD. Writing platinum or palladium, I'll pick platinum for this one, means that now the reaction can proceed. And here's what happens. During the reaction, it actually follows the mechanism we talked about a few minutes ago. Essentially, we're going to break the double bond and change it into just a single bond. The R groups that were already attached to the carbons will remain where they are. But essentially, the double bond opens up, leaving a single bond in its place and creating space for two new bonds. Each one of these bonds will now go to a hydrogen. So the net result of this reaction is that you start with an alkene molecule and you end with an alkane. This can also turn unsaturated molecules, including unsaturated fats, into saturated fats. Let's try an example. Here's a typical way that you'll see an alkene hydrogenation reaction written. Go ahead and pause the video and write what the final product should be. When you draw the product, technically you can draw the product using an expanded structure, a condensed structure, or a line structure, but it's most customary to draw it in whatever way the reactant was given. I gave you a line structure, but if that's confusing, don't hesitate to draw it out in more detail. Essentially, because I know I have a carbon on each side of this double bond, I'm going to break open the double bond, and I'm speaking metaphorically, of course, and that will create two new bonds where I can attach the hydrogen. That means my final product will have a single bond in its place, and the rest of the molecule will remain the same. Now, strictly speaking, I don't need to actually write the hydrogen because we know that hydrogen are implied on a line structure. So this is a fully correct answer. If that weirds you out a little bit, it's okay for you to actually draw in the hydrogen. So I could draw this structure and add the single bonds to the hydrogen because remember, as we said at the beginning of the quarter, the best version of the structure is the one that makes the most sense. If you draw this lower version of the structure, most chemists would understand that you did that just to communicate that that's where the two hydrogen were added. Now let's look at another type of an alkene addition, the addition called halogenation. As you already know, a halogen is an element from group 7 on the periodic table. And as I mentioned previously, even though the halogens contain the elements fluorine, chlorine, bromine, iodine, and astatine, most of the organic reactions that involve them work with either bromine or chlorine in their diatomic form. In a halogenation reaction, we do almost the exact same thing that we did in hydrogenation, except instead of adding H2, we add Br2 or Cl2. Halogenation reactions don't require any catalyst. So for example, if I wanted to do a halogenation, let's try drawing one in a different way. Here's the line structure for an alkene. Go ahead and do a chlorination reaction of the alkene, meaning the addition of Cl2. To add Cl2 to this molecule, there's essentially two things I have to remember. First, I have to redraw the molecule without the double bond, because addition reactions break the double bond and turn it into a single bond. Now I have to add a chlorine to each carbon that was touching the double bond. I'm putting them on opposite sides of the zigzag just because it looks convenient. We're not going to go into a lot of details about how the mechanism of this works. In fact, we won't go into any mechanism details, but if you're wondering about the geometry and which way things point, the mechanism is usually what explains that. Again, since we're not going to cover that in this class, you can usually just write the atoms in any way that looks best on paper. So in this case, I pointed the Cl up on one of the carbons and down on the other. This brings us to a third type of addition, and things will get a little bit more interesting with this one. In this third type of addition, we're going to do a process called Hydrohalogenation. We've already seen hydrogenation and we've already seen halogenation. So guess what this reaction will be? This is the addition of a molecule that contains both hydrogen and a halogen. Again, specifically, we tend to see chlorine and bromine as examples of our halogens most often. So hydrohalogenation usually refers to the addition of HCl, hydrochloric acid, or HBr. Again, this type of reaction doesn't require a catalyst, but it is a little bit more interesting because we have two different atoms to take care of. Here's an example. If I bond two carbons together, and we'll keep this as a very simple molecule, let's say I add to this solution HBr. We can automatically predict that the same type of addition mechanism will occur, and in that process we'll break the double bond, leaving a single bond in its place. The hydrogen that were already attached will still remain, and now I get to attach the hydrogen and the bromine. In this example, because there's basically a mirror image between the two sides of the molecule, it doesn't matter which carbon gets the hydrogen and which carbon gets the bromine. The same would be true if we were adding HCl. Sometimes, however, you do have a more important choice to make, because sometimes whether you put that halogen on one carbon or the other will actually give you two different products. So let's look at an example where this happens. I'm going to draw the structure for a slightly more complex alkene. To draw the structure, I'm going to connect these carbons to the double bond, and then I think on this side I'll just keep it nice and simple. Since we did an HBr reaction on the last page, let's do an HCl, hydrochloric acid, reaction on this page. Go ahead and draw the product that results. As you worked on this, you probably noticed you had to make a choice about where to put the hydrogen and where to put the chlorine. Basically, you have to decide which carbon gets which atom, because we know that we have a carbon on each side of the double bond, but unlike on the last slide, these carbons aren't connected to identical atoms and branches. So in order to determine what the correct way to actually add the H and the Cl to this molecule is, we have to use something called Markovnikov's rule. Markovnikov's rule is one of the most famous rules in organic chemistry, and it's a really simple one to remember. When you're breaking a double bond in an alkene addition, you always add the hydrogen to the carbon that already has the most hydrogen. It's a little bit like it wants to go bond with the carbon that has its friends on it, metaphorically speaking. So we'll add hydrogen to the carbon that has the most H, and then the other atom, in this case Cl, or if it was Br as on the last slide, we're going to add that to the carbon that has the least hydrogen. So let's look at the molecule and decide which that is. When we start, the carbon that I have here on the left is bonded directly to the double bond. It's also bonded directly to a carbon and another carbon. So this carbon is actually bonded to 0 hydrogen atoms. Now let's look at the carbon on the right side of this molecule. This carbon, and if it's hard for you to see it, remember you can always re-sketch this molecule in a slightly different fashion. This carbon is bonded directly to a carbon on the right side, and it's bonded to one hydrogen up above it. So it has one hydrogen. Our Markovnikov rule says we add hydrogen to the carbon that has the most hydrogen already. So in this particular structure, I'm going to keep the backbone of the structure the same, but I'm essentially going to leave off the double bond. Here's what the molecule looks like when I break the double bond. Now I have two new bonds I get to draw. One will go to hydrogen and one will go to chloride. Because we said the carbon on the right already has one hydrogen, which is more than the carbon on the left, that's also where I'm going to bond the new hydrogen. The carbon on the left side was not attached to any hydrogen, So instead of bonding with the hydrogen, it's going to bond with the chlorine from HCl. This product is what we call the major product, or sometimes people just call it the Markovnikov product. It means it's the product that followed Markovnikov's rule. Depending on the exact molecules that you have, you'll get a mix of the major product, which has the chlorine bonded to the carbon in this image, and the minor product, where we would switch where the chlorine is bonded to. The major product might be major in the sense that 99% of the molecules are like that, or in some cases it might not be such a majority. It might only be 60 or 70%. In most cases in this class, I'll always ask you to only draw the major product. And this is another classic example where we would probably leave the minor product off completely because it's not what we intended to get from the reaction. Let's try one so you can get some practice. Here's a molecule. If you were to add HBr to this molecule, draw what the major product would be. To determine the major product, or the Markovnikov product, I'm going to use Markovnikov's rule. Markovnikov's rule says that I bond the hydrogen to the carbon that has the most hydrogen, and I bond the bromine to the other carbon. My carbons in question here are the ones on each side of the double bond. Looking at this top carbon first, how many hydrogen is it bonded to? Well, like the example on the last page, this carbon is bonded to another carbon, and another carbon through the double bond. So it's not bonded to any hydrogen atoms. The carbon on the lower part of the structure, however, has a carbon bond here, a carbon bond through the double bond, but notice there's only 3 bonds drawn. That means there's a hydrogen that's implied by the line structure. So like on the previous page, this carbon actually has 1 hydrogen present. Because of this, I'm going to bond the hydrogen from the HBr to the carbon that already has 1 hydrogen on it. If you didn't figure that out already, go ahead and pause the video and draw your final product. In my final product, I want to make sure I keep the backbone the same because all I've done is essentially broken the double bond into a single bond, and I want to attach the bromine to this carbon. Whether or not you show the hydrogen on the other carbon, this carbon here, is up to you. This brings us to our last type of alkene addition, which is what's called a hydration reaction. Not surprisingly, hydration reactions are just the addition of water, or the addition of H2O. And one way to understand these better is to remember that water as a molecule can be thought of as an H and an OH. So much like we already looked at HCl and HBr, pretty much the same mechanism will hold true here. Hydration, however, does require a catalyst. This is one reason that you can't mix unsaturated fat with water and get some type of a neat chemical reaction. It won't happen unless you have a catalyst present. And the catalyst that's required is one of the most common catalysts in organic chemistry, H2SO4. In other words, sulfuric acid. So when you mix sulfuric acid, water, and an alkene together, you get an addition reaction. The addition reaction will follow Markovnikov's rule because, again, in this case we have an OH instead of a Br or a Cl. So for example, if I had this structure, a double bond between carbons, and let's put some carbons on this side, here's how it would look. Water as a reactant, sulfuric acid as a catalyst, commonly written like this above and below the arrow. Go ahead and draw the final product. Again, there's 2 possible products, but the Markovnikov product, or the major product, is usually the only one we'll write. Looking at my 2 carbons, the carbon on the left side has 2 hydrogen attached to it, whereas the carbon on the right side has no hydrogen attached to it. That means I'm going to attach the hydrogen from the H2O to the carbon on the left side of the molecule. The result is this. I have a new hydrogen attached to that carbon, a single bond, and on this side I have the remaining carbons that were already present along with a new group, OH. This would be my final product. It's an example of my major product or my Markovnikov product, and it's the one most scientists would be looking for. The last topic I want to talk about in this lecture is a really interesting one because it's the subject of polymers. We'll talk about alkene polymers specifically in a minute, but first let's talk about what a polymer actually is. People have a lot of different perceptions about what the word polymer means. In chemistry, polymer is any molecule that has a regular repeating structure. I tell people it's a little bit like you had a stamp of a molecule structure and you just stamped it end to end to end over and over and over again. That stamp itself, that particular part of the structure would be what's called a monomer. A monomer means one thing. And when we take many monomers over and over and over and join them together, we have a polymer, many things. Generally, we don't talk about a molecule as being a polymer unless we're talking about thousands of monomers, usually tens or hundreds of thousands of them in a chain. So while these molecules do have a start and an end somewhere, we usually only focus on what the repeating pattern of the chain is. One other thing about polymers, they are awesome. It is one of the best topics, in my humble opinion, to study because it's fascinating. It has an insanely large number of real-world applications. It has the ability to make people sick and make them well, and you could probably save the world if you became a pretty good polymer scientist. Of course, that's just my opinion, but what I want you to know is when most people think of the word polymer, they just think about plastic, like a plastic bag. And the fact is, polymers are in just about everything around us, including in the human body. There's a lot of different stuff in the human body that qualifies as being a polymer. So don't brush aside polymers and just think they're plastics. Polymer science is fascinating. It's a good thing to go into if you like chemistry and you want to make a lot of money. The reason is there are so many applications of it that directly affect our day-to-day lives. One of the things that makes polymer science so interesting is how we manipulate what the physical and chemical properties of these polymers are. The properties of polymers depend on a bunch of different factors, but the main ones are these. Of course, it depends on what your monomer actually is. Different monomer structures will give you different polymers, and those will behave differently. So we'll see in a couple minutes that what makes a plastic bag or plastic wrap different from the solid plastic you might sit in a chair, or something you don't even think of as plastic, like Kevlar or clothing, depends on the structure of the monomer. Another thing, though, is how the monomer chain branches. We've seen that something as simple as an alkane can have branches. Well, when you start to deal with thousands and thousands of pieces coming together, there can be some pretty interesting differences in their branching. The last thing, which is kind of the downside to looking at polymer science, is the topic of plasticizers. Plasticizers are additives. They're compounds we add to polymers to manipulate their properties. So if you made up a polymer in the lab and you decided it was a little bit more rigid than what you were looking for, you might add a plasticizer. Plasticizers are really just mixed into the polymers, and that's part of the problem, is while a polymer is a molecule that's chemically bonded together, and therefore it tends to stay together, plasticizers are just mixed in, and therefore they're able to leach out of some polymers. So there's a lot of plasticizers that end up in the news because of their health concerns, and that's typically because they're older, less well-researched compounds that people really didn't think would be in as many applications as they are today. It can be a pretty scary topic, so don't be afraid to ask questions if you do have them. But for now, let's just look at one very small realm of polymer science, which is alkene polymers. The reason we talk about alkene polymers at this point is because alkene polymers are really just alkene molecules that have been added to each other. So instead of adding together HCl and an alkene, or H2O and an alkene, we'll add an alkene to another alkene, and then do it thousands of times to get a polymer. So you take one alkene molecule, and if you mean to draw this on paper, you'll add another one, and another one, and another one, and so on. Here's the general process. In order to show this effectively, what I'm going to do is draw the carbon-carbon double bonds, and again, I'm just going to use R groups. These could be methyl groups, ethyl groups, longer and more complicated chains, or they really could even just be a simple hydrogen atom. What happens in an alkene addition is when we have two of these alkene molecules next to each other, and for now we'll just pretend they're the exact same type of molecule, what will happen is the carbon-carbon double bond breaks, and in that process we actually form a new single bond between the molecule. I'm going to change my pen color so hopefully you can see this in a little bit more detail. Essentially what will happen is this double bond will break and the electrons that were in it will be transferred to a new bond. Now, both of the electrons don't go in the same direction. One goes one way to create a new bond and the other goes the other way. So from this, we start to form a new bond. It's only half of the bond though. This is why we need two molecules. On the adjacent alkene, we'll also break the double bond, and right away you can see where this is going. The electrons split apart and we get a new bond forming on the other side. And so these two bonds come together. This is where our new single bond forms. The same thing would continue to happen on both sides of the molecule, again for thousands and thousands and thousands of alkenes. The resulting molecule would have multiple monomers put together. We usually draw it as simple as possible. In this case, I have, let's label these, carbon 1, carbon 2, carbon 3, and carbon 4. I'm going to put them together. I'll change the color for the new bond. We had used a green color before, so I'll do that again. This single bond is our new single bond. So instead of adding hydrogen or HCl or any of the other examples we've talked about, I've added this new bond. What's connected to the carbons is the same thing that was always connected to them. These are groups. So when I draw this, I need to make sure that everything has remained attached. Now I would continue to form new bonds, but at some point I'm going to get tired of drawing this molecule. So what we usually do when we have a polymer is we pick the simplest repeating unit possible. A very typical thing in alkene polymers is just to look at 2 carbons at a time. Again, to make this clear, what we would do is use parentheses. By putting parentheses through the bond, we're indicating that you're just going to repeat that structure over and over and over. That repeating structure is your monomer, and everything within the parentheses indicates that's the monomer that will repeat over and over and over again. We'll do an example in a second, but first let me mention one thing. Depending on what you start with, that's usually how we name the final product. We're not going to learn any sort of technical IUPAC naming for these polymers because that's not what most people do. For instance, if you start with a molecule like ethylene, we would call the polymer that results polyethylene. Or if you start with propylene, you'd get polypropylene. Let's see this in an example. Draw the polypropylene polymer, which starts from the monomer 1-propene. To do this correctly, you want to start by drawing 1-propene so you're confident about what it looks like. Then line up at least 2 1-propene molecules next to each other so that you can connect their double bond. Don't be afraid to move things around geometrically until it looks right. Pause the video and start it again when you're ready. Okay, so I asked you to do something that's a little bit challenging here. And the reason is 1-propene is an alkene, but it's an alkene that has 3 carbons in the molecule. So let's start by drawing 1-propene. There's a couple different ways you could draw it. In condensed form, which you've probably noticed is the way I like to draw things, 1-propene would look like this. If you drew it in a more expanded form, it might look like this. The carbon on the left side has 2 hydrogen, then there's a double bond, and we have a hydrogen and a CH3. Either one of those are correct. But here's one thing about drawing polymers. We're going to want to connect this double bond to another one. So when I actually start to work on this, what I recommend doing is draw the double bonds first so that they'll be conveniently placed next to each other. Then draw in the rest of the details for the molecule. For instance, in this case, I know I'm going to need the carbon double bond, so I move that third carbon out of the way. I'll do that on both of my structures. These are both completely correct ways to draw propylene, and therefore it sets us up to easily draw the polypropylene polymer. I'll just draw two monomers. I'm going to break the double bonds and form a new bond in the space between them. That new bond will be a single bond, as will everything that's left over. Of course, I basically have half a bond that's ready to form on either side of the first and last carbon. So when I draw my final product, here's what I draw for two monomers. I draw a carbon single bonded to a carbon with the methyl group. This was basically the skeleton of my first propylene monomer. Then I connect that to the second propylene monomer. Again, I fill in the important hydrogens and other carbons, and that left me with my parentheses on each side. Now, strictly speaking, this is two monomers put together to represent the polypropylene polymer. And again, because it was called propene, the old-fashioned name for this was propylene. It's not something that's really used by IUPAC standards, but as a result, we tend to call this polypropylene. Again, we're not going to get into the naming on polymers because common names are so standard and IUPACs just aren't used that often. One more thing about this. Generally, a chemist will always choose to use the simplest structure possible. You can either guess that that's because we're efficient or that it's because we're lazy. In this case, notice that I had two monomers. If I wanted to represent this in the simplest way possible, I could actually delete an entire monomer off of this structure. I don't recommend you doing that on your homework just because it makes it a little harder to see how the molecule actually formed, but this would be totally correct for an organic chemist to read. Usually we put a little n, meaning repeat this some number of times. If we know how many times we need it repeated to get a particular type of molecule, we might write that number there instead. Let's look at a couple examples of alkene polymers. There's actually a lot of common polymers that are formed from alkenes. You're going to recognize most of these. The one we just did, polypropylene, consists of a propene monomer, and polypropylene is actually recyclable plastic number 5. So if you ever flip over a container and see a 5 on the bottom, it's very common with things like yogurt containers and margarine containers, you're holding polypropylene in your hand. If we drew out a long version of it, we'd see that it just forms a zigzag. Notice that it doesn't have any double bonds. The double bonds were present in the monomer before the polymer formed. Examples of polypropylene include rigid plastics, such as those that are used in plastic chairs and plastic desks. But depending on the plasticizers and the amount of branching that takes place, you can also make softer substances. Things like rope are very, very commonly made out of polypropylene, and in fact a lot of types of clothing, especially those that are used as thermal long underwear because they dry quickly, are made out of polypropylene. Another very common polymer, which is actually even simpler than polypropylene, is polyethylene. Ethylene is actually an old term that predates IUPAC nomenclature. It really just means ethene. So when you take two carbons bonded together through a double bond, that's ethene. And when you bond them into an alkene polymer, you have a really long chain of carbons. It's really not that interesting of a structure. But interestingly, the way it forms dictates how this can be used in our day-to-day lives. Depending on exactly how we put together this polyethylene structure, we can get either high-density polyethylene or low-density polyethylene. High-density polyethylene, or HDPE, comes about when the polyethylene molecule doesn't branch. It looks just the way we'd expect it to, one carbon after another going in chains of thousands and thousands of atoms. The consequence of that is that we basically get one long zigzag, and we can put it right next to another identical molecule, another zigzag. Because there's not a lot of branching, if any, you can pack them very tight together. That's why we call it high-density polyethylene. The consequence of this is that we get very rigid materials that are made out of HDPE. So we think of these usually as plastics that are used in rigid containers, things like shampoo bottles or cleaning bottles. That's HDPE, and it's recyclable plastic number 2. Chemically, it's identical to LDPE, or low-density polyethylene, but they differ solely in the amount of branching that takes place. Low-density polyethylene arises when the different monomers start to connect in ways that cause branching to happen. As the branching happens, the molecule grows larger, and it gets harder to pack it right next to another molecule or another polymer. It's sort of like trying to gather a bundle of sticks when there's still all sorts of twigs pointing off them in all directions. It's hard to pack them together efficiently. The result of this is that low-density polyethylene is not rigid. It's a much more flexible material because the molecules can't pack themselves very close together. We usually think of LDPE as being used in items such as plastic shopping bags or plastic wrap that we put on our food. It's recyclable plastic number 4. And think about how interesting this is, that even though we have the exact same molecules, the branching alone makes the difference between a shampoo bottle and plastic wrap. Interestingly, Saran wrap, the trademark plastic wrap, used to be made out of another polymer, but due to safety concerns, it was changed to polyethylene, which is widely considered to be non-toxic. We could talk about polymers all day. I know you'd like that, but I know you also have other things to do as well. So let me wrap this up just by showing you a few quick structures of some other common polymers. Polyvinyl chloride, or PVC, is actually also a polymer that comes about from an alkene. It's probably most famous for uses in things like PVC pipes and insulation. The only difference between PVC and polyethylene is the presence of a chlorine atom attached to one of the carbons. It's recyclable plastic number 3. Polystyrene is probably most famous as styrofoam. And polystyrene is like polyethylene, but again with one substitution. It has a very special type of cyclic structure attached to it called a benzene ring, which we'll be studying in our next lecture. Polystyrene is recyclable plastic number 6. And even though you think about it as things like styrofoam, packing peanuts, and other styrofoam-like material, it's also used in other types of plastics such as CD cases. I want to sneak one more polymer in here because it's polytetrafluoroethylene. It's essentially the polyethylene polymer where the hydrogens have been replaced by fluorine atoms. PTFE is one of the most interesting polymers, in my humble opinion, because it's one of the reasons we have things in our modern lives like Teflon and Gore-Tex, basically non-stick waterproof substances. It's also something I did a lot of my graduate research on, so trust me, we're going to come back to it later because it's really interesting. That's where we'll wrap up this lecture. Our last lecture in this section will focus on the molecules called aromatics. In the meantime, let me know if you have any questions.